So in this simulation, we basically produced sustainable aviation fuel by utilizing carbon dioxide and hydrogen. So to run this simulation perfectly, properties and in our property section, we can see that we have defined these components as our simulation in our simulation, and in the method is basically the common method, and the base method is based upon the Penn Robinson method. So if you go to the simulation process, simulation flow sheet, define different things here. So our process basically start with the carbon dioxide, which is basically captured from the industrial emissions, and this carbon dioxide firstly compressed into carbon, and then it cooled and mixed with the hydrogen in a mixture, and after that it passed through the RWGS reactor, and in this RWGS reactor it's basically designed as a equilibrium reactor which has some typical temperature and pressure, and also the stoichiometric reaction here we have given here. We basically convert carbon dioxide and hydrogen into carbon monoxide and water. After that, we have designed this block. These are the cooler, flash, and the separator are basically normal things. The separator is basically separates the water and other gas streams. But in this B12 block, which is basically um, a thing, a block that basically controls the hydrogen to carbon monoxide ratio, which is basically very important for the Fischer-Tropsch reactor. In this Fischer-Tropsch reactor, we basically designed it as a stoic reactor, defined some temperature and pressure, and the reactions are defined based upon the fractional conversion ratio. And these fractional conversion constant things are basically um, defined from the literature review of many articles and papers. Um, these fractional conversion rates are basically depends upon the temperature and pressure. So if we change the temperature and pressure, we should and we must define those the fractional conversion again. Then afterwards, we designed this hydrocracking reactor, and this hydrocracking reactor basically a stoic reactor also, and in this reactor we also temperature and pressure is defined, and the reactions are defined also based upon the fractional conversion, and this fractional conversion is basically defined upon different literature review again. And this hydrocracking reactor basically converts the higher hydrocarbon like C30, C20, C16 to the lower hydrocarbons actually. And this fractional conversion also depends upon the temperature, like if it is 420, then there has some different there has some fractional conversion. If it is less than 420 or greater than 420, then the fractional conversion will be changed actually. And after that we have defined a very long separation techniques for separating different streams like sustainable aviation fuel, naphtha, and other residues from our main streams actually, main product streams. So in this SAF separation techniques, we have defined it as a separator, which basically have some splitting ratios. Like we have defined 94% due to some limitations of the components, and we have defined here from C8 to C16 as our sustainable aviation fuel ranges, which is basically very typical. Again, it's defined from the literature actually, C8 to C16 as the sustainable aviation fuel. After that, we have defined another strains, which are basically naphtha and residues. So if we just see the results, it's pretty interesting. Like yes, we can see here we have got almost 518 kgs of SAF, which is basically produced from 3500 kgs of carbon dioxide. So yeah, this is the whole thing. We can convert the carbon dioxide into SAF. Thank you very much.